These are the notes for 7.3 Part 2. If for any reason you were not here on the day we did 7.3 Part 1, make sure you've watched that because you're going to need to know some of those things to complete this. So this is basically multiplying radicals continued. And we're going to mainly just do a bunch of examples. So the first example we're going to do is I'm going to give you a function in function notation. So if f of x equals the square root of 3x squared minus 6x plus 3, what we want to do is find a simplified form for f of x. So we're going to find a simplified form for f of x. So pause if you need some more time to write that down. So what we want to do if we are trying to simplify something in a square root is we want to break it down into its factors. So we're basically just trying to factor that expression in the square root. So remember, our first rule of factoring is to take out a common factor if possible, and I believe we can take a 3 out of everything. So I'm going to factor out a 3. I'm left with x squared minus 2x plus 1. So I divided each of those terms in the square root by 3, and I pulled that 3 out. Now, it's still in there. Don't forget it anywhere. So now let's see if we can factor this part in the square root. So when I look at that, I'm recognizing that the first term and the last term are perfect squares. The square root of x squared is x. The square root of 1 is 1. And if I check, the middle term is negative 2 times x times 1. So that means that that part in the parentheses is a perfect square trinomial. So that means that in the inside of the square root, I still have the 3, but that part in the parentheses factors to x minus 1 squared. Minus because we had a minus right there. So now if I look at what's in that square root, remember that a square root and a square cancel each other out. So this square root, since I can break it up, this is equal to the square root of 3 times the square root of x minus 1 squared. So I just broke this up into two different square roots, because we can do that if they're being multiplied. So the square root of 3, I can't simplify it all. It's going to stay in the inside, the 3. But a square root and a square cancel each other out. So the x minus 1 gets to come out, and then I have to multiply that by the square root of 3. You could write the square root of 3 before it if you wanted. It would actually kind of make a little more sense that way if you wrote square root of 3 times x minus 1, but either way is fine here. So factor and try to find perfect squares if you can, or perfect cubes, like the sum of cubes or difference of cubes if it's a cube root. Alright, let's do some more examples, similar to the ones we were doing on the previous notes. So all we're going to do on these next two examples is simplify. On the first one, we're going to simplify the square root of x to the 7, y to the 11, z to the 9. So we're taking a square root here. So remember, we could do the tree method. It's going to take a long time if we try and do that. So you don't have to write this, but x to the 7 is x times x, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. It's a square root, so I'm looking for pairs of guys to come out. So those would get to come out. Now here's the thing. I don't want to do that for y to the 11. I don't want to write out 11 y's. So sometimes when these numbers start getting bigger, we want to find a different method to do this. So remember that if something is squared, like if we have the square root of x squared, a square and a square root cancel each other out. This is just x. So what we want to do is see if we can break these factors up. The factors are x to the 7, y to the 11, and z to the 9. Let's see if we can break them up so that we can write it as something squared. Maybe just take part of it out. So let's see. You've got a square root here. I'm going to do the x. I'll do that in red. So it's a square root. 7, I cannot write 7 as something squared. You know, like if I did x to the 3 squared, that would give me x to the 6. So I can't think of anything that times 2 that multiplies to 7, at least not a whole number, right? So let's see, if we maybe break that up though and do x times x to the 6th, I could write that x to the 6th as something squared, right? I'm going to work on the other letters in just a second. I could write that as x times x cubed squared. So I broke the x to the 7 up into 2 factors, and then one of those factors I could make it something squared. Let's do the same thing with the y. So y to the 11, I can't write that as something squared, but if I separate it out into y times y to the 10th, I can write y to the 10th as something squared. So I can write that as y times y to the 5th squared. And then z to the 9 is similar. Let's do that one in blue. I can write z to the 9 as actually z times z to the 8, because that's a 1 plus 8 is z to the 9. And then I can break that up as z times z to the 4th squared. So now I look at what things can come out and what things can stay in. So inside my square root is going to have to stay any of these things that were not a square. So x, y, and z. On the outside, I can cancel these squares with the square root. So that cancels and this gets to come out. X to the 3 gets to come out. Y to the 5th gets to come out. And then the z to the 4th gets to come out. So this is my answer here. I didn't have to write that square root symbol quite so long. All right, so I think that's maybe the best way to do it. Another way you could have looked at this problem if you're really confused right now is if we're doing, I'm going to restart it over here, the square root of x to the 7, y to the 11, z to the 9. You could remember that a square root is the same as taking all of that to the power of 1/2. And then we just distribute that 1/2 to everything. So x to the 7 to the 1/2 is x to the 7 halves. This is going to be y to the 11 halves. And z to the 9 halves. I just multiplied all of those by a half. Then maybe I could write those fractions as mixed numbers to help me see it a little better. So this is x to the 3 and 1/2. This is y to the 5 and 1/2. And then this is z to the 4 and 1/2, right? So that means that, I know this is kind of weird. That means that anything with a whole number we can bring out. So we can bring out the x to the 3, y to the 5, and z to the 4. And then we still have the 1/2 left on all of those. So the power of 1/2 means in the square root. So in the square root, we're going to have this x, this y, and this z. It's whichever way you prefer, really. You get the same answer. Honestly, I'm not sure how well that one works with other, not a square root. So let's try another one here. So for this example, we're going to do the cube root of 16, a to the 7, b to the 14. Alright, so on these ones, when I'm getting these big numbers as exponents in here, I don't like to use the tree method on those, like I just talked about, but I still like to use the tree method on any numbers. So I like to do the tree method. We're looking for a cube root here, so I'm looking for groups of 3 to come out. So 16 is 2 times 8, 8 is 2 times 4, and 4 is 2 times 2. So you just make that factor tree down as far as you can. And then I'm looking for groups of 2. Groups of 3, because it's a cube root. So these 3 2's can be friends, and one can come out. This guy's got to stay on the inside of the cube root. So if you want to make note for later, we're going to have a 2 coming out and a 2 on the inside. The 2 came from here, the 2 on the inside came from there. Now let's talk about the a to the 7 and b to the 14. So remember, we're trying to write these as something to the power of 3. So I can't write 7 as like something times 3, but I could write 6 as something times 3. So I'm kind of just going down through the numbers. 7 doesn't work. 6, ooh yeah, 6 works. Because I could write that as, let me do the a down here. We're trying to figure out the cube root of a to the 7. I could write that as the cube root of a times a to the 6th. And then I could write the a to the 6th. I could write that as a squared cubed. So that means that this a has to stay on the inside, but this a squared gets to come out because it's cubed. That part's going to go away. So this is a squared coming out. This a is staying on the inside, so cube root of a. So we can add that to part of our answer. A squared times the cube root of a. A squared's out, cube root of a is in. Now let's do the same thing with the b. So we're trying to find the cube root of b to the 14. So let's see, 14 is not anything times 3. 13, no. 12, yes, 12 is something times 3. So I can rewrite this as the cube root of b squared times b to the 12, because 2 plus 12 would take us back to 14. Then I can't do anything with the b squared. He's just kind of sitting there. But I can write the b to the 12 part as b to the 4 cubed. Because 4 times 3 would get me that 12. So this b squared has to stay on the inside. But the b to the 4 gets to come out because he's a perfect cube. So now if I look at all this stuff that's got to go in my answer, I'm going to have a 2 on the outside, an a squared on the outside, and a b to the 4th on the outside. And then inside my cube root, you know what, that's looking a little too close together. Let me write it down here. 2a squared b to the 4th on the outside, 2a squared b to the 4th. And then on the inside of my cube root, I'm going to have 2a b squared. This came from 2a b squared. And that's my answer. I know these are a little confusing. I honestly kind of would have rather to do this in class, but we'll go over any questions you guys have. All right, let's try. Honestly, these next ones are easier than those. All right, so for these examples, we just have 3 more examples for this video. We're just going to multiply and simplify. So for the first one, we're going to do the square root of 15 times the square root of 6. Now, either of those numbers, I can't find the square root of them, and I don't even think that I can simplify them anymore. Like 6 is 2 times 3. There's no groups of 2 to take out. So sometimes it's easier to actually multiply these together and then try and simplify the square root. So I can put these into one square root and just do 15 times 6, which is 90. Now let's try breaking down the square root of 90. So I like to do the tree method. So 90 is 9 times 10. You could have also done 45 and 2. You can do whatever you want. 9 is 3 times 3. So there's a pair that gets to come out. I'm looking for pairs because it's a square root. 10 is 2 times 5. None of those are going to come out. So you can either box both of those and have 2 times 5 on the outside. Or you can just be like, all right, I know I'm going to have 10 on the outside. So 10 stays on the outside. Or sorry. The 10 is the one who didn't get to pair up, right? He stays on the inside. The 3 had a pair, so he gets to come on the outside. So that's your solution to that one. All right, 2 more. This one is going to be 3 times the cube root of 25 times 2 times the cube root of 5. So get that one written down. Now on this one, we have these numbers. Everything's just being multiplied. Doesn't matter what order we multiply in. Let's go ahead and multiply, though, these numbers on the outside. 3 times 2 is 6. And then since these are both cube roots, I can put them into one cube root, 25 times 5, which is 125. Then, I'm kind of hoping we know in our head that the cube root of 125 is just 5, right? So this is just 6 times 5, which gives us an answer of just 30. That's it. That one simplified really nicely. All right, one more example. Last one. It is 4th root of 8x to the 3, y to the 5th, times the 4th root of 4x squared, y cubed. So right now it might be difficult to find the 4th root or to simplify either of those at all, but since they're both 4th roots, we can multiply them and put them all in one big 4th root. So in here, let's see, 4 times 8 is 32. X to the 3 times x squared is x to the 5, because I'm adding up those exponents. And y to the 5 times y to the 3 is y to the 8th, because I added up 5 and 3. Now let's see if we can simplify this at all and find any groups of 4 that we can pull out. So let's see, 32 is 16 times 2. 16 is 4 times 4. And each of those 4s is 2 times 2. So I'm looking for a group of 4. So I've got 1, 2, 3, 4 2's that can, a 2 can be pulled out. This 2 is going to have to stay on the inside. So if I want to start writing the parts of my answer over here, I can. A 2 comes out, and then 1, 2 stays on the inside. All right, let's deal with the x's now. So we're doing the 4th root of x to the 5th. The 4th root of x to the 5th. I'll do that over here. We want to see if we can break that x down and find something we can write it to the power of 4. So let's see, 5, no, nothing times 5 is 4. 4, yeah, that works. I'm just going down the numbers here. So I can rewrite x to the 5th as x times x to the 4th. So that means that this first x is going to have to stay in, but this is a group of 4 x's. 1, 2, 3, 4. X to the 4th is x times x times x times x. That gets to come out. So 1x gets to come out from that. 1x has to stay in from right there. So an x is going to come out, and an x is going to stay in. And let's look at the y's. Y to the 8th, and it's the 4th root of y to the 8th. So I'll do that down here. The 4th root of y to the 8th. Well, I think I can automatically go ahead and write 8 as 4 times something, right? I can write the 4th root of 8 as the 4th root of y squared to the 4th, because 4 times 2 would get me that 8. So the 4th root and the 4 cancel out, and I'm just left with y squared who gets to come out. So a y squared gets to come out, and now we're going to put all this together into one answer. So on the outside is 2xy squared. 2xy squared. On the inside of my 4th root is 2x. And that's my solution. Alright, if you have questions on these, it's okay. This is a really confusing topic sometimes. So just come to class with questions.